Okay, so let's start off with, so you guys are telling me it's a positive hydrocarbon. Okay, what is the process of it? What is it that makes it kind of unique compared to just being a positive hydrocarbon? How do we get to that state? Okay, so which of the following carbonations would expect to rearrange? What is rearrange again? And why do we rearrange? What is the significance of it? Why does it happen? And what usually is a catalyst of it? And actually, I believe this is where we left off. And I remember correctly, Israel had answered one of these questions. So if there's a branching, okay. Okay. So are you saying that the double bond is between the branch, or and then the cation occurred there, or you? Okay. Yeah. Okay. So like a tetra or tertiary structure. Okay. Oh, nice. Okay. Good terminology. Okay. Okay. So which one of these would we expect to go through rearrangement? How about A? And can you tell me what type of carbocation it is? You guys know what I mean by what I'm asking for. Is it a primary? Is it a secondary? Is it a tertiary? Those are kind of the questions that you guys are going to get on the exam. Was that? Okay. So it's a secondary. Okay. So do we expect this to go through rearrangement? Okay. Why not? I'm trying. Okay, so let's take a step back. You guys don't remember any of this? Oh yeah, you were sick. And even when you were here, you were sick, so yeah. Okay. So here's an example when we start talking about the carbonation, all right? So in this case, we have a double bond, and then we have the hydrogen bromide as one of the reactants, right? So then we know that the double bond is going to be providing the electrons to the hydrogen bromide, right? So we'd get the formation of these two products, right? Okay, now if you take a look where the products are located, one is going to be located here, and one is going to be located here. So we would assume that the bromine would occur. This major product is our surprise product, right? We'd assume that the bromine initially would occur at this point. But instead, because we had that methyl group, right? We had that hydrogen that's here off that carbon, right? That hydrogen can be exchanged and be delivered here instead, and then we can end up with the bromine on that tertiary carbon. Hence our major product here. Okay, now why? So this here is this is going to be a 1,2 hydride shift. So this is a rearrangement. So again, the double bond is going to be delivered the electrons to the hydrogen bromide, or specifically the hydrogen. So then the hydrogen is going to be initially, we think is going to be attached to this point. So we get that hydrogen attached to this carbon, allowing that double bond to be disrupted, and we get a plus charge. Then the electrons here are going to be delivered to the bromide. And so we have the bromide. So this guy doesn't go under rearrangements, where this one will. Okay. So what happens here is that we get a shift between that secondary, the hydrogen on the carbon here, and that hydrogen is going to be transferred to the carbon, this carbon. So we'll get a shift of that hydride being shifted over to this guy. So then this guy becomes positively charged. That guy becomes a neutral charge. Okay. Now, the reason it does that, because we know that this guy has better stability than having a charge out here. And so based upon that stability, it's a lot easier for it. So we'll get, as Simpula was saying, we'll get an sp3 formation here because of stability purposes. Okay. Or sp2, sorry. Okay, then the bromide then will attach here, again, for stability reasons. So the majority of the product will be here in this rearrangement. Okay, now the same thing could happen here if we have, let's say, a methyl group here instead of a hydrogen, right? So we could get a 1,2 methyl shift. Same premise. Double bond is providing the electrons to the hydrogen. The hydrogen is then providing electrons to the chloride to form the chloride. So we get chloride forming. We'll get a hydrogen added on. The hydrogen is going to be added on to the terminal carbon. Easier one to add on to. So then this intermediate is going to form. This methyl group is then going to be transferred or rearranged to that carbon. Now, once that methyl group transfers over, this guy becomes positively charged. The chlorine is going to then attach there, balancing out the charge on that. And then we're going to get, this is our major product. Okay. So, and the key is that this is going to be the minor product. The majority of the species are going to be this, because you're going to have more of the rearrangement occurring because stability purposes than this. Okay. And the stable structure is going to happen faster than this structure, right? And because when we talked about kinetics, you guys remember us talking about kinetics and speed of the reaction, right? So if it's slow, if it's a slower reaction, you're going to have less of that product being formed. This here is a slower reaction formation. This formation is much slower than this. Okay, and that's mostly because of stability purposes. Okay. Okay, so here, so we added an additional carbon. So see the distinction between here, between this this ternary carbon. The double bond is like literally adjacent to it. Where here we actually have another carbon, not this one, sorry. Here we have another carbon in between, right? So it's a lot harder to sit there and transfer that hydride or that methyl group over if there is another saturated carbon between them. Okay, so it won't be able to do that. So you're not going to get that formation. Okay, so in that case, the only product that you're going to get is this product. Does that make sense? You're not nodding your head, Jessica. That means you have questions. You don't see the distinction. Let me do a little drawing so it'll be a little more apparent. Okay, we have basically this saturated carbon. Okay, in between a ternary structure, right? Or ternary carbon. Where if we go back to the last one. The ternary carbon here is directly adjacent to the double bond. Okay, so in other words, we don't have that saturated carbon in between. So you can't, it's kind of like, have you guys ever played telephone? Right? So you can tell, I can tell him something, right? But I'm not telling him something. Okay, because, and it's reliant on him to do the next step. But if there's nothing to tell, then, you know, it's like I tell him, it stops at that point, right? Okay, so it's not like I'm going directly to him. So I can't skip him because that's what telephone works. I tell him, he tells him, you know, and so I can't skip him. I have to tell him, I can't go directly to Mauricio and tell him, right? So, and that's the same thing that's happening in this situation, right? So we have this guy. Well, this guy can be moved here, next, adjacent to it, but he can't skip over the person in between. Does that make sense? Yeah, yeah, kind of like leapfrog. You can't leap over two people, right? Because that's really hard, okay? And it is, that is actually a very good analogy. It's really hard to leap over two people. What was that? A whole lot of energy, right? Yeah, and chances are you're gonna fall on your face afterwards, right? And you're not gonna be too happy about that. Okay, so that's exactly the same thing that's happened here. So you're not gonna have that happen when you have that saturated carbon between. You guys know what I mean by saturated carbons, right? That's right, single bonds, good. Okay, so now that we've had that refresher, you guys can help me. So which one of these will we expect it to be a result of our rearrangement? Or okay, you said D as in donkey. Okay. Let's see. Oh, it was you who answered this one. Yeah. So B. Mm-hmm. That's right. That's right. That's right. That's right. Do you see that? Okay. So what was that? So the correct answer is B and E. Okay. So as he nicely pointed out, this guy is too far, right? Remember, we're talking about that person in the middle, right? So that's not going to happen. Okay. Here we have the positive charge here. So this one is going to be a perfect case for rearrangement, right? So In other words, we're going to remove that plus charge and transfer the hydride there. Okay, see, it's right where it's supposed to be already, so we don't have to worry about moving it. It's the most stable point. Same thing with D, most stable point. Right? E, perfect case for a rearrangement, right? So here we move that methyl group, you know, or a hydride, in this case, not a methyl group, we could move another hydrogen over. And then F, there's no need to. Right? It's already stable. Okay. Okay, so then boran as an electrolyte. I'm sorry, electrophile. Okay, so when we talk about boron, we know that boron, when it forms its structure, it has an incomplete octet. Okay, so when hydrogen forms its structure with that H+, it's also going to have that incomplete octet. So it's going to act, they're going to act very similar to each other in terms of it. So in this case, boron, that boran is going to act as if it's going to act just like the electrophile, just like that cation, the carbon cation. Yeah. Okay, so in this case, we're going to take advantage of that intermediate. We're going to actually use that boran. Boran is a hydrogen boron, or right? Boron hydride, hydrogen boron hydride. So boron hydride is boran. That is its common name. BH3 is called boran. This is common. You're right. Trihydrogen boride. Or that's right. Thank you. Oh, okay. Yeah. Old age. Okay. So in this case, the first step is that you're going to be using the boran, and these guys are going to kind of act like a catalyst. They're going to help initiate the process, right? So, and when we do that, we're splitting up that double bond, and we get the formation of an alcohol. Okay. So in this case, that OH is going to be replacing the electrophile. Okay. It's going to be replacing the boron. So you guys remember when we talked about the acids as a catalyst, or we're using hydrogen sulfate or sulfuric acid. I'm rusty today. Sulfuric acid, you don't remember that. We talked about it beforehand. Okay, again, at the end of the day, the sulfuric acid is going to be used as a catalyst. It's going to accept the electrons, right? And then you're going to end up with the hydrogen and plus added onto it, but then that's going to allow the water molecule to be added on, okay? And so again, the OH is going to be, in this case, is going to be the nucleophile. And under these circumstances where the OH here is going to be the electrophile. It's going to replace. Okay. So how does this work? Okay, so the boron here is going to act as the electrophile, but the hydride is going to act as the nucleophile. The electrons are going to go to the boron. The boron is then going to allow the hydrogen to share its electrons, right? And then we're going to get the formation of a hydride, or the addition of a hydride here. And you're also going to get the formation of the alkyl Borad. Okay. So then, and this basically just shows you so much of what we were seeing with the hydrogen bromide, or the bromic acid, or hydrobromic acid. Then it's going to actually obey that same rule. So then we're going to have an sp carbonation that's going to be occurring in this location. So this here just basically shows us the charge that's going to be associated. So here we're going to have a partial negative charge. This guy's going to have that partial positive charge. This is basically showing you that disruption. These guys are going to have interaction, but it's going to have more stability associated with it being on that, the hydrogen being on that center atom, other than the hydrogen. I mean the boron being on the hydrogen being on the hydrogen being closest to the methyl group, compared to the boron being closer to the methyl group. And we know that because steric hindrance, right? You guys are familiar with steric hindrance. We kind of mentioned on it before. Do you guys remember what steric hindrance is? No. We're talking about something else. So steric hindrance is, okay, so let's see. Okay, so I'm going to be fine, right? Right here. And I'm going to you. I'm going to you. Okay. So, okay, Caesar. Okay, so me and Caesar are bonded. Okay, so I'm going to bond to you, and then I'll just come here. You're going to bond to me, and you're going to bond to me. Okay, now I want you guys to bond to Justin. Both of you guys. Now you guys got to spread out a little bit closer. Spread out to the spars. Remember, the way it works is, you guys. Okay. So, and we want to be as far away from each other as possible, but at the same time. Okay. So now you guys see. Now look how close they are, right? So Mauricio's kind of screwed, isn't he? But he's like right next to Jesse, right? So steric hindrance is the fact that, oh, they can't see that. That's all right. They don't need to see. So yeah, turn it around. Yeah. It's okay. I'll explain it to them. Yeah, you can go ahead. Turn it around. Okay. Okay. Were you turkey? No, can't. Okay. Okay, now you see, there we go. Now, see, these guys have to be as far away as possible, right? But what happens is that these guys are going to start running into each other. There's exactly, right? And so because the way that we have the structure is, it's going to be less stable. They're going to be constantly bumping into each other, kind of bumping each other, and so that's not going to cause stability, right? And so it's going to be a less stable structure. Okay, so you guys can go. Okay, because it's going to be a less stable structure, it's not going to want to happen, right? So we want stability. We want something that's going to end up stable. Okay. And that's what this is just basically showing you. This guy's going to be less stable because these hydrogens here are going to kind of interfere with these hydrogens, right? Because they're going to be spread out. And you got to think about it. When we're bonding, we want room to move, right? We don't want to be sitting right next to somebody. We don't, they're not your boo. You don't want them all cuddled up with you. So you want your room, right? Okay, so in this case, we have, as I say, 3 potential hydride ions, okay? So double bond goes here. The hydride is going to attach here. And that makes sense, right? So that means the boran is going to attach here. Are you with me? You have that look. Okay, because of stability purposes, because you have, remember, this is a center carbon and you have the 3 hydrogens around it. If you had that borad here, it has that borad and then it has its own hydrogens that would be interfering, right? And you want to try to minimize that interference. That's steric hindrance. Okay. Are you guys there? Or did you guys chime out?
We're here.
Yeah.
Okay. You guys see our crazy structure? Yeah. No?
Yeah.
Yeah.
Okay.
Although I don't have these notes.
You don't have these notes?
No.
Well, a lot of you guys don't have these notes, so it's okay.
Okay.
You'll get them when you
Wait.
come back.
Oh, okay. Or I was just gonna say if you could post the PowerPoint.
I could do that. Yeah, I'll do that as well. Okay. Oops. Okay, so now this also is going to be the effect when we actually have hydrocarbons attached to the borad. Okay, so R represents that hydrocarbon. Okay, so that's going to be exactly the same thing that's going to be happening in the case of that. Again, we want to try to minimize steric hindrance, and so you're going to go to the point where you're not going to get as much steric hindrance. Again, we're looking for stability. Okay, and then that's the same thing if we have a dialkylide boron. Okay, and you guys know the difference. Di meaning 2 hydrocarbons, and they don't have to be the same ones. They don't actually have to be exactly the same. It could end up being 2 different ones. Okay, questions, concerns? Cash, Kool-Aid? Okay. So only 1 hydride ion is going to be needed for hydroboronation. Okay. Okay, so in the case of your alkali boron, it's going to have a preference for the carbon that has the less substituted sp2, or is the sp2 carbon. It's going to have a preference for that carbon that's going to be less substituted. Okay, so it's always going to try to find the one that has the least substitution, that doesn't have so much stuff around it. And you guys know that because of steric hindrance, because of stability. Okay. So this guy is called 9BBN. Okay, so this guy is 9 boron bicyclo 3.3, 1 nonane. Okay. So why is it called 3.3 nonane? Okay. Okay. So we know that, like you said, the boron is attached, doubly attached. So we have the boron attached here, the boron attached here, right? And we have the hydrogen attached at the top. Okay. So, and that's where you get your bicyclo. And where's that? The 3.3? It tells us what? 3.3, 3.3.1.
One skeleton and then the other one that is attached that way separately.
Okay, so you're saying this single skeleton, meaning there are no name.
Like it's folded in half.
Mhm.
I don't know.
Okay.
They're connected, but they're unseparable.
They're counted independently, you're saying?
Yeah. But that's counting out together and 20 carbons.
Yeah, it's 9 carbons, right? So we got the 9 carbons, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Okay. So the 3.3. Okay.
And then we starting from the other side. So corner starts with 1
Uh-huh.
and then 2, 3 upwards, and then going downwards starts with 1 again, 2, 3.
Okay. So you're saying because the structure itself. Yeah, you're making reference to the.
Yeah, I know.
Yes. Okay, so that's correct. So your structure is represented by the 3, 3, 3, right? So your 3 carbons that are going to be attached to that hook structure, since it's a no name, and we have a steric structure associated with it. You guys remember we were talking about like the chair and the yes. So in this case, since we have that no name structure, we also have to give how many points are going to be responsible for the structure that we're having. So you have 3 and 3 points that are going to be added on. And then you have technically 1 in a single plane representing a plane structure. Okay. And so that kind of gives you an idea of what the steric structure of this is going to look like. Now, but the key part of it is that it's going to try to find the place where it's going to have the least amount of substitutions, right? And that is not going to interfere with anything else. So the boron, if you take a look at the boron here is going to have a preference for this spot rather than closer to that 3,3 point or anywhere on that 3,3 point, because you're going to have more steric hindrance there compared to what you're going to have in the center. Does that make sense? Okay. And that's the purpose of that. Okay. You will be naming these structures. We'll work on it yet. We haven't gone over the nomenclature yet. Just relax. We'll get you there. Yes, you're going to be responsible for naming as well. So it'll probably be up on the final. Yeah, because your upcoming test is already up. Second exam or third exam? Yeah. And you're not going to have a fourth. You're just going to have the final. Boy, you guys hear some incredible stuff. There's a third one. Yeah, you should have already a third one up. Yes.
Is it on Chem 101?
It should be. Is it not up? It is up. The third one. Exam 2 is already up. Okay. Exam 3 is showing up. Okay. I need to fix that. So your exam 3 should be showing up.
And is the exam 3 the group one?
I'm not going to give you guys a group exam this semester. I'll save it for next semester.
Oh, okay.
Yeah. What was that? Yeah, it's going to be Chem 101, no group.
Wait, so we're having another exam this week?
The practice didn't show up either? Okay, so I need to fix that. Pardon me?
We're having another exam this week?
Not this week. It's going to be, it's technically should be open already, but it's for next week. It's due next week.
Okay.
Okay, so I'll figure out what I did wrong. Anxiety. Okay. Okay, yes. It is going to be consisting of everything that you've learned up to this point. All of chapter 6. Is going to cover all of chapter 6. So it's going to be this chapter, right? I'm going to put the homework assignments up for chapter 6. You're going to have the end next week to get it done, the exam. So you'll have the weekend to essentially get it done. And then I'll have to look over the final to see exactly what all we covered of the material. Okay, so let me take a step back. So what? You guys have the practice, the handout thing from last year practice exam. Yeah, and you guys should be working on that diligently every week, right? As we go over the material. You're not going to get a practice for that. You just got to come in and I'll tell you, I will steer you in the right direction. Don't worry, I'll steer you right. I'm never going to steer you wrong, right? And so all it is, I mean, if you know how to do crystallization, I'll give you guys a substance. You guys are going to go through that process of crystallizing it, and you should be okay. Yeah. No. Yeah, it's going to give you the instructions on how to go about that process. And so then it's going to be based upon the purity that you guys get of your substance. It's going to be an unknown substance. You're going to have to purify it, and then you're going to identify it based upon its boiling. Well, yeah, it's going to be here you go, you do it, but no, I'm going to give you procedures. Well, yeah, right now I have to give you procedures because you guys haven't learned a lot of procedures. Well, technically, they're all pretty much the same, right? So far, what you've done, you guys would say it's pretty standard. Okay, so you heat, you're cool. You heat, you're cool, right? And then you dry, heat, and cool. Hopefully, I will have something to allow you to dry fast so that you guys can determine your substances pretty fast. So. There is going to be written questions on multiple guess. Yeah. And it's going to be as you go through the process. No, you're doing it in groups. You guys are doing the whole thing in groups. yes. Yeah. Because we don't have enough equipment for you guys to do it independently because we only have 6 of all the glassware. So we're kind of limited. So, not yet. What was that? There are 9 people in the class. So technically, although one of them is going to be MIA during that time period, she won't be back yet. She'll be back after you guys. So what I'll do is I'll put you guys in either groups of 2 or 3. And I'm going to do a random die shuffle. Right? I pick your groups. Okay?
Dr. Henry, so will the fill-in questions be for the lab practicum?
Yes. So the questions, you will have multiple choice and fill in questions for the lab practicum. Yes.
Okay.
Yeah. And you guys will have access to your notes that you guys, of your formal lab procedures that you guys have used before. And okay. Oh, I love giving you guys tons of questions because that means I can make it as hard as I want to, right? Yeah, you could do that. You could, you know, that's your prerogative, yes. But we're not gonna have all day to do the exam. Okay. I'm just letting you know. Okay. 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 Yeah. Okay. So the process of when you have these alkalides, right? The trialkalides or the dialkalides, it's going to be the same process, right? And so it's going to go through that same mechanism as when we had the halide. I mean, yeah, the hydrides, as we had the hydrides. You know, I'm thinking halides. So again, the double bond is going to be acting on the boron. Now, you guys know when we talk about the hydride is going to have that negative charge associated with hydride, right? Okay. So in this case, that's the distinction that is different from the bromide when we have the hydrogen bromide and that. So because in the case of that, it's the same mechanism, but the target is going to be slightly different. Do you understand? So like, let's take this up. I get that look that you guys don't, you're not hearing me. Okay, so here, right? So this was the addition of the hydrogen bromide, right? So in this case, that double bond is going to be acting on the hydrogen, right? Then the hydrogen is going to then transfer the electrons over to the bromine. Then the bromine is going to become bromide, right? It's going to have that negative charge associated with it. The hydrogen is going to have a plus charge associated with it as it goes to the carbon. Okay, now here it's going to be just the opposite, right? Because the electrons are first going to be transferred to, instead of the hydrogen, is going to be transferred to the boron. And then the boron is going to transfer those electrons to the hydrogen. And so that hydrogen is going to end up having that negative charge, and then as it attached, okay? Where this guy is going to end up having that positive, you know? Does that make sense? The bond between HBr, it does break, you know, and so you actually have it actually end up forming the bromide ion. It's the same thing that happens with the bond between the boron and the hydride. It's actually going to form hydride, which is a negatively charged hydrogen, right? Okay, same thing's happening here. This guy's going to form a negatively charged bromine, so it's going to be bromide. So you actually get a breakage of bond. They're just showing you because it's, oh, go ahead. Yeah, yeah, because like I said, so they're still showing you the double bond, right? So this represents, this is just a nice way of showing you the double bond is going to be transferring its electrons to the hydrogen. Well, the hydrogen doesn't want to be negative in this case because bromine wants negative, right? Because it's more electronegative. So it's going to have that pull associated with it. So then it's going to then transfer the electrons over to the bromide or bromine to form bromide. So then you're going to get that bond being broken. And then the bromide is going to form. So that's what we saw earlier when we were talking about the halides, that are the formation of alkaline halides, right? Okay. Yeah. Yeah. And so this is kind of a little different because it's the double bond is being transferred over to this guy. Then this guy, the boron, is transferring the electrons over to the hydrogen, and then the hydrogen is going to come back here and attach here because it's a negative charge. Okay, makes sense? Okay. Okay, now that's going to be exactly the same process that we're going to see when we have, let's say, methyl groups on the boron, right? And so in this case, we're going to get the formation of our tri-alkylide Borad, because it already has those, let's say, methyl groups, and then it'll have the other halogen that is now attached to. Okay. The mechanism is exactly the same. Okay, double bond transfers the electrons to the boron. The boron transfers the electrons to the carbon. Boron transfers electrons to the hydrogen. Hydrogen then connects to that carbon. So, okay. So hydroboronation followed by oxidation. So that first thing is that we're going to get that formation of our alkaline boran, right? Or in this case, this will be the trialkyline boron. And then we could have oxidation occurring with any of these molecules. Don't fall asleep. You're up too late. Caesar, did you keep them up? Okay. So here we could have hydroxide, we could have peroxide, or we could have water. All three cases are going to give us essentially the same products. Okay. The only thing that is your byproducts are going to be slightly different. Okay. So you're going to end up with hydroxide. Okay. Okay. Or in that case, we're going to get the formation of an alcohol. Okay. Okay, so, and we know that this is called oxidation because you're getting more formation of carbon oxygens, okay? Kind of like burning of hydrocarbons, you get carbon dioxide, right? So that's oxidation as well, okay? Okay, so, so if we had the peroxide, so this is the hydrogen peroxide ion. So in this case, we've already lost one of the H plus. Okay. So in this case, the electrons are going to be transferred over to the boron. So then it's going to be directly attached to the O, and so then it's going to transfer those electrons back to the oxygen. That oxygen is going to then transfer it to the OH. Right? So, and again, we're going to get a shift occurring. We're going to get that 1-2 shift. So, and instead of having that plus charge now, we're going to get the state that boron actually likes, because it doesn't like to be in that tertiary state, right? Because it likes the attachments. So, and thing is that this guy is going to then reattach the hydroxide is then going to reattach to the boron. And again, boron doesn't like to be in that state, so you're going to have a negative charge. Those electrons are going to then be transferred over to the oxygen, breaking that bond, because again, that tertiary state is not its primary goal. It doesn't like it. So then those electrons are then added on to, in this case, water. And then the hydrogen is going to be transferred over. It's going to transfer the electrons over to the hydroxide. And then we're going to end up with the hydroxide ion, and we're going to end up with an alcohol. Okay. Questions? Okay, so these are the products that we're going to expect from our carbons, right? Under both circumstances, we're going to end up with the same product. So we're not going to have a carbon cation rearrangement. Okay, so if we add the addition of bromides, bromines and chlorines. Okay, so yeah, here or here, 45, yeah, 45 or 35. Oh, okay. Okay, I have the extras. Okay. This here is going to be the final product. It's still here. I mean, it's just, you already have this formed. So you're going to have boron attached to the OH group, right? And then what's going to end up happening is that this is going to exchange with, let's say, hydrogen, or so you're going to end up reforming your bromide ion. So let me explain. Yeah. Okay, so let's go back. Okay, so you're going to have this guy. It's still going to exist in solution, right? The thing is that this guy isn't as stable, right? So it's going to end up interacting with, because you have hydroxide in solution, you have peroxide, right? So remember your peroxide ion. Okay, now your peroxide ion does not start off as a peroxide ion. It actually starts off as hydrogen peroxide, period. Right, so that means it has two hydrogens associated with it. One of those hydrogens is lost. And so what's going to end up happening is that hydrogen is going to end up replacing this guy. So you're going to get the reformation of your hydrocarbon, and then you're going to have an H attached to this part. And you're going to have the hydroxide ion as another product. Do you understand? No, what you need to be concerned about is the hydrocarbon that's forming, right? So this guy, the hydrocarbon, this guy, not your alkaline, your alkaline or your boron alkaline product, okay? Okay, so you're going to have to be concerned about the hydrocarbon that we're looking at, or the organic molecule that you're forming, the alcohol in this case, right? So in all of these cases, you're going to end up with an alcohol. That's what's the major product that we're looking at. This is the organic molecule that we want. See, the alcohol, right? So that's what we're primarily concerned with. Everything else is just means to get to that, okay? So, and what we're using hydrogen boronation to get us to that point. And so really what you have is you have H plus that's attached to this guy, because this guy is our hydrogen peroxide ion, right? Okay, now there's really an H plus that's still present. That H plus is going to be utilized here, right? You're going to have H pluses that are going to be utilized here. One is going to be responsible for replacing the hydroxide, and the other one is going to be reforming the water. Okay, so because you're going to have an abundance of your hydrogen, your H plus in solution. Okay, so again, your electrons are being transferred over to the boron. Well, the boron really doesn't want them. He cares less about them, right? So it's going to sit there and say, okay, well, I'm going to use this bond here that I have, and I'm going to have it attach, or its electrons are going to be used to go here. Okay. So that means that this hydrocarbon here, that's down here, now is going to be transferred over to that oxygen, right? It's going to get that shift. Okay. So then the electrons on the oxygen are then going to be transferred over here, right? So then we're going to get the formation of the hydroxide ion, because it's giving up those electrons. Okay. That first part. Okay. Okay. No, there's more. And there's more. Right. And that's why your flashcards are going to come in handy, because they do a pretty good job of going through this. They skip some of the steps, but for the most part, they get most of them. Because all of these are relatively, if you notice, they have those arrows, meaning that they can go either way depending on how much product is being made. And that's going to be important too, right? So depending on how much of stuff that you have in solution, that's going to affect the drive. Okay. Now, the other thing is that these are intermediates, right? So it's going to be pushing one way hard one way, or hard the other way, right? So you're not going to see them too long. They're not going to last that long. Okay. So as you can see here, the electrons here then are going to come back, and again they're going to reattack or transfer it to the boron. Okay, so then you're going to get an attachment, and we know that boron doesn't like to have 4 things attached to it. It only likes to have 3. It likes to be incomplete, right? Unlike carbon likes that. Boron is like, fuck, no, I don't like that, right? So it's going to try to find a way of getting back to where it is. So what's going to happen is that, okay, so I have that OH there. So now it's going to use the electrons here, and then it's going to transfer those over to that oxygen, right? So now I have an oxygen that has a charge, a negative charge associated with it. Okay, so it's going to take those electrons that's negatively charged to separate water, break the hydrogen off of water, so then we can form an alcohol. So it's going to take the electrons here, right? It's going to break apart water, right? So it's going to split water. So then it's going to get H, the hydrogen, H plus. It's going to transfer the electrons, are then going to be transferred over to that oxygen, causing this to be an hydroxide molecule. That's what we get, hydroxide, and we get an alcohol. Water is provided in the reaction. Yeah, so all of these, okay, so we have to think about it. We have an aqueous solution. Anytime that you have, first off, you have peroxide, you're gonna have an aqueous solution, right? Because most peroxide is never 100% peroxide, because peroxide, it basically breaks down to water, right? So, in most cases, we can get high percentage of peroxide, but you're never gonna get 100% peroxide. Do you understand? So like typically the highest percentage peroxide that you can get is about 30%. So that means 70% of it is water. And do you guys want to know why? Peroxide is unstable, right? So if we let peroxide sit long enough, that peroxide is going to decay and it's going to end up being water. Okay. And so regardless of what you have, that means that you have all of these moieties in solution, right? You have water, you have peroxide, and you have your hydroxide. Okay. So typically there's more water molecules than anything else, right? It's like I said, 30% is the highest that you're going to get. Okay, so that means 70% of it is water, right? Or roughly 70%. You also have hydroxide in there, and then you have a little bit of hydrogen ions that'll be in there as well too, right? Okay, two-step process, right? So the first part is you're going to have the formation of your boronation, right? So it's just going to be adding the boron to it. That's the first part, right? So the first part is adding the boron to this, okay? So once we get the boron added to this, then the second step is the addition of peroxide. You could just add peroxide solution in general, and you're going to end up getting, okay? So together, right, it's called boronation oxidation, right? Because we're adding oxygen to, okay? It's a two-step. Does that make sense? So that's the reason why it's written 1, 2. Okay, so the first step is boronation or boration. The second step is the oxidation. It's just, THF is just a, it's hydrofluoro something. It is just a catalyst, right? Yeah, it just helps the process happen faster. That's all it does. It doesn't really get involved in the reaction itself. Well, it does, but it doesn't. It's not you don't get a product from it, right? So you get it exactly the same thing at the end. Okay. Uh-huh. Yeah, so those guys, because it's hydrogen peroxide solution, right? So it's going to be water, it's going to be the hydroxide, it's going to be the hydronium ion, it's going to be, even though they don't have the hydronium ion, it's going to exist, but they show it as just H2O, right? Right, as your peroxide. What happens as soon as you put the peroxide in solution, the hydronium ion dissociates. And so you end up with just the hydrogen peroxide ion, which is the negatively charged version, right? And then the H plus is in solution. Okay. The hydrogen peroxide is the one that's reacting. Because that's right. So we go through that process. Oops, wrong way. Hold on. So it's the hydrogen peroxide that's going to be the reacting component. But the hydroxide also reacts. It reacts at a different step. But we also form hydroxide. We form more hydroxide. What do you think this is? This is just hydroxide. Okay. Do you get that? So you got to remember that we're working with an aqueous-based solution, right? And regardless of what we can't do, hydrogen peroxide is always going to be an aqueous-based solution. So you're going to have all those components in your solution, right? So, and they just list them all out because they all kind of play a part, right? If you think about it, really the ones that we know that are playing a part that we are paying attention to is the hydroxide ion, it's the peroxide ion, and it's water, right? Because we go through our steps. Peroxide ion. Okay, blah, blah, blah. Oh, we get the hydroxide ion, right? We also form it, but we're also utilizing, right? It's a twofer right there. Okay, so we're forming some, but we're also going to have some in solution, which is going to be easier. And then we get down here, water, right? So all of them play a part in this process. Okay, and the funny thing is that over time, you're going to just reform a lot of those products, right? Because we know we form hydroxide ion, right? And if we paid attention, if we did everything completely, we'd get the reformation of water, right? And we'd get the reformation of the hydroxide ion. It's all a nice little cycle. So at the end of the day, you're just getting, you won't get a complete balance because you're going to lose some of them because you're forming an alcohol product, right? So it's not going to be exactly a one-to-one that you're going to get back, but you're going to replenish some of those products. Does that make sense? Until you start running out. Okay. Do you guys see that? Caesar? You can't fall asleep. I know it's rough. Old Chem is not the easiest. There's a lot of mechanisms. Okay, so let's take a 5-minute break. Okay, and then you can take a mesa break, and then I'll see you guys back here in 5 minutes. I don't even know what time it is. 2:30. Okay, we'll say 10 minutes. Okay, you guys 10 minutes. 10-minute break, guys. Okay, so what we're gonna do is, since I can't teach and teach, so we will, I will see you guys on Wednesday. How about that? We'll finish lecture on Wednesday. Yeah. Abby, are you guys there? Can you hear me?
Yeah.
So I'll see you guys on Wednesday, since and it might be a whiteboard lecture next week. I mean on Wednesday. So we'll finish it up on Wednesday.